Hello everyone, and welcome to my channel. This channel is for educational purposes, and we look at some of the great theories of everything that I've encountered in my research that you probably don't know about because they've been suppressed. And today is our 451st video on the reciprocal system of theory from Dewey B. Larson. And the reciprocal system of theory is also known as the universe of motion. In 1959, Mr. Larson proposed his two fundamental postulates, which include 7 assumptions about how the universe operates. And then he elaborated those assumptions on with a process of deduction, kind of a if this then that approach, and arrived at a theoretical universe, how the universe would look if his postulates were correct. And then in some of his books, he compares his theoretical universe with the measured empirical universe of the scientists that they compiled in their tables. In particular, in chemistry, we're looking at his book here called Basic Properties of Matter, that look at some of the basic properties of matter, like the melting point, although he doesn't really get into the melting point exactly here. It gets right up to very close to the melting point, but also the specific heat and the compressibility, the interatomic distance, many of the qualities of electric and magnetic effects, isotopes, and things like that. So we are looking here at chapter 6, that's called Specific Heat Patterns. We started this chapter a couple days ago, so we're right in the middle of it right here. But he's talking about some of the patterns of specific heat. Specific heat is really the amount of heat that you need to add to something in order to increase it by a certain temperature. Kind of just like the rate of heat that you add. In Larson's universe of motion, he's always looking at rates and derivatives of things. Now, Larson's two fundamental postulates lay all this out. The first postulate has 4 of the assumptions. The universe is composed entirely of one component, motion. So the universe is made out of motion, not matter, not energy, not force, but motion. And in particular, Larson identifies a specific kind of motion called scalar motion. This is a motion that has a magnitude, but it has no specific direction. And a model that you can use for scalar motion is a balloon that you put dots on. And if you blow up the balloon, all the dots will be moving away from each other. If you want to add an extra dimension to that, you could also use something like raisin bread, where you cook the bread, all of the raisins will be moving away from each other. They won't be moving in any specific direction. In fact, they'll be moving in all directions. Every dot will be moving away from every other dot. Every dot will be moving in every direction. So there is no specific direction. If you suck in the balloon, all the dots will be moving toward each other, but again, in no specific direction. So that's the foundation or the source from which Larson creates his universe. And so when you accept the idea of a universe of motion, you have to be able to accept the idea that motion comes before everything else. So motion precedes the thing that would be moving. So you have to be able to envision motion of nothing, motion without anything moving. Larson calls that outward motion the progression, and the inward motion calls gravitation. Now, the next postulate, or the next assumption, is that motion has two reciprocal aspects, space and time. So motion is basically a relationship between space and time. It turns out motion is basically a fraction, with space or time as the numerator and time or space as the denominator. You can see this in speed. The bike is going 10 miles per hour. 10 miles of space and 1 hour of time. Space over time is speed. And you can see the reciprocal relationship if you decide to double the speed. And you could say the bike is now moving 20 miles per hour. 20 miles of space and 1 hour of time. Or you can say the bike is now moving 10 miles per half hour. 10 miles of space and a half hour of time. So two equivalent statements can be arrived at by multiplying the space or by dividing the time. So that's a reciprocal relationship between space and time in speed. Larson extends that from not just speed to all of our scientific phenomena, such as matter, energy, force, acceleration, power, pressure, and so on. All of them are relationships with space or time as the numerator and time or space as the denominator. Speed is space over time. Acceleration is space over time to the second power. Energy is time over space. Matter is time to the third power over space to the third power. And these come in one part from the third assumption that space, time, and motion all come in 3 dimensions. And so you end up where you can have the exponents of space and time being up to 3, really up to 6. In such cases like density is mass over volume. And so matter is time to the third power over space to the third power. Density is mass over volume. Volume is space to the third power. So density is space to the third power. Time to the third power over space to the 6th power. So you can really get up to the 6 powers of your exponent of space and time in those fractions. But if you have, you can have 3 dimensions of space and 3 dimensions of time in really 1 dimension of motion. Now you can say, if you are looking at that expanding balloon and you decide that you're going to declare a reference point, and you're going to arbitrarily say that this particular dot is motionless, and once you do that, you're basically stopping the world, and you're basically able to make measurements now. You're able to determine directions, and it looks as if all of the dots are basically in a force relationship with that reference dot. All of the dots look like they're moving away from that dot, like there's a force of repulsion between them. Or if the balloon is being sucked in, that there's a force of attraction between them. But this, what Larson calls as-if force, is only a product of you choosing the reference point. That is, the direction is not part of the scalar motion. It's part of you choosing the reference point. And so when you do that, you either will assign a spatial reference system or a temporal reference system. Your spatial reference system is what Larson calls coordinate space and clock time. You have 3 dimensions of space in x, y, z coordinates in a still frame. You're basically anchoring yourself to space, and so space becomes still and a still background, and time still has its scalar motion. Time is getting later and later and later, progressing or flowing, but in no specific direction. And you could have also the reciprocal of that. In the right environment, you could have a temporal reference system where you have 3 dimensions of time in a still frame, and you have clock space. Space is always getting farther and farther and farther apart, but in no specific direction, like on the surface of an expanding balloon. Now, in both cases, the spatial and temporal reference system, you need all 3 of those dimensions to describe 1 dimension of motion. So when you're talking about 3 dimensions of motion, you're talking about a reality that exceeds the capabilities of the reference system. You don't have a reference system that can properly describe 3 dimensions of scalar motion. Now, the 4th assumption is that space, time, and motion all come in only discrete units, meaning you have to have a full unit of space before you have space. You have to have a full unit of time before you have time. You have to have a full unit of motion before you have motion. Turns out 1 unit of space is approximately 2 millionths of an inch. 1 unit of time is approximately 1.52 times 10 to the minus 16 seconds. And 1 unit of motion is 1 unit of space per 1 unit of time. Remembering that speed is space over time. So that's what Larson calls unit speed. 1 unit of space and 1 unit of time. And that is the rate of the progression. So the progression is outward at 1 unit of space per 1 unit of time, which Larson also calls the speed of light. So the progression, he calls that the progression of the natural reference system, outward at the speed of light in all directions. So we have the spatial reference system, we have the temporal reference system, and then we have the natural reference system, which is a moving reference system. So this is nature's system. This is the system that nature actually conforms to, outward at the speed of light in all directions. And that is always there, omnipresent and eternal. And it's, in the background of every calculation, every measurement that you're going to be making, there's always this initial unit of the progression of the natural reference system. And it is the source, the 0 point, the neutral point or the null point of this universe, meaning that half the universe is moving slower than the speed of light and half of the universe is moving faster than the speed of light, which is anathema to legacy scientists, but that's what Larson calls the cosmic sector. The material sector is the slower sector. That's the sector that we're familiar with and the scientists are comfortable with. But they are inverses of one another or reciprocals of one another. In the material sector, you have coordinate space and clock time, the spatial reference system. In the cosmic sector, you have the temporal reference system, coordinate time and clock space. And when you cross the boundary, the rules invert. That speed of light boundary, the rules invert, and now the roles of space and time interchange. Now, within both the cosmic sector and the material sector, you have a inside region that has to do with the discrete unit postulate as well, a unit of space inside the material sector, when you have atoms and particles that are interacting in what appears to be less than 1 unit of space, or when they reach that unit of space separation, they can't get any closer together because you have to have a full unit of space. So what they do instead is they do the equivalent of that, is that they move further apart or outward in time. And by moving apart in time, they are doing the equivalent of moving closer together in space. And we see it as moving closer together in space because we only see space and we don't see time in the spatial reference system that we're anchored to in this sector of the universe. And so Larson calls that the time region. It's the region inside a unit of space. If you don't have a full unit of space, you don't have space. And if you don't have space, then you only have time because the universe is made out of space-time motion. And so now there are some, when you cross that speed of, when you cross that unit space boundary, then the rules invert again. And now we see the progression as inward in space and gravitation as outward in space. But we're not really seeing space. We're seeing equivalent space. We're seeing, because what is really happening is that the events are occurring in time. But we don't see them that way. We see the reciprocal of that in space. But the equivalent space has a few different caveats that you have to keep in mind. When you cross a boundary and look into a different region or sector of the universe, you have to apply the interregional ratio, which is kind of like how much you're losing in the translation. And so it's a small fraction. You only can really see a small fraction of what's going on. And what is an equivalent space is a second power entity. So we see the second power of this reduced event. The same is true in the cosmic sector, except in the cosmic sector we have the space region within a unit of time. The progression is moving things closer together in time. Gravitation is moving things further apart in time. And if we go back to the time region in the material sector, when you reverse those roles, it creates an equilibrium where atoms and molecules will get closer and closer together in equivalent space. Those forces will be balanced. The forces of progression, the inward force of the progression, and the outward force of gravity will find an equilibrium spot. Larson refers to that as the interatomic distance. And there's a whole lot of other stuff, obviously. The last 3 postulates are really kind of axiomatic as far as doing math and science, even though they are disputed, and I would disagree with the last one, and maybe all 3 of them. But they are that the universe conforms to the relations of ordinary commutative mathematics. The universe's primary magnitudes are absolute, and the universe's geometry is Euclidean. Okay, now let's get into a little bit of this work here on specific heat patterns. Now I'll try to catch you up to what you might not know. This is a detailed study, and this is not something that you're going to pick up right away. You're just really going to try to glean various principles and ways of thinking about the reciprocal system just to see kind of how it works. The main things that you really need to just keep in mind are that, the general universe of motion and the different regions of the universe and the postulates, but then just kind of how Larson applies it. The reciprocal system is a system of theory, so it can be applied to any subject once you understand the general principles. He's applied it to chemistry here, but he has books on physics and astronomy and economics and metaphysics. And it has been applied to other subjects as well by some of his associates. Um, but really, the study of the reciprocal system is difficult. It's really like detective work. You have to just kind of accept the fact that you don't understand a lot of it, and hope that that he says something later on that might clear it up. That happens quite often. So you just have to be able to kind of accept the fact that you're a little bit confused about things, and you just piece it together a little bit at a time. Larson did a great job of putting this stuff together, but he's only one person working for, really, he worked on this for 60 years until his death in 1990. And, but one person can only do so much with a theory of everything. When you're trying to put it into every subject, and he's having to come up with a whole new language, new terminology, new terms. Cut him some slack, and give him the proper respect of just, instead of disagreeing with him out of hand because of something unfamiliar, say, okay, well, maybe he knows what he's talking about. Let's just move on. Okay. All of the types of deviations from the regular pattern that have been discussed thus far are found in the electronegative elements of the lower rotational groups. Okay, so that's toward the top of the periodic table on the right-hand side. There is also an additional source of variability in the specific heats of these elements, as their atoms can combine with each other to form molecules. The result is a wide enough variety of behavior to give almost every one of these elements a unique specific heat curve. Okay, now Larson comes up with equations for these basic properties of matter, including the specific heat, but in many cases he comes up with a number of equations because different atoms, depending on where they are located on the periodic table, kind of have different characteristics, and different factors have to be taken into consideration. Of special interest are those cases in which the variation is accomplished by omitting features of the regular pattern. The neon curve, for example, is a single straight line from the minus 1.32 initial level. Again, the initial level, that is considering only the progression of the natural reference system. And also the photon, which the photon is at the core of all of the atoms, because that is how you basically get atoms, is by taking that progression of the natural reference system and reversing it so that it becomes gravitation, where it's an inward progression. That is done by taking that outward motion and rotating it back in 3 dimensions, or really you vibrate it back in 3 dimensions, and that appears as if it's a rotation. So Larson's periodic table is a combination of motions, 2 two-dimensional rotations and one-dimensional rotation that appear in ABC sequence. A and B are alternating, and C is optional. In the noble gases such as neon, it is 0, and it can also be positive or negative. And so for the electronegatives, it is negative, and for the electropositives, it's positive. Okay, so the neon curve, for example, is a single straight line from the minus 1.32 initial level. That's really the level represented by a photon. Photon is a vibratory unit, and so it can be positive or negative in this case. In this case, it's negative initial level to the melting point, a single straight line. Now, a lot of the specific heat curves have segmented lines. They go through various transitions as they are heated up from, from absolute 0 up to, the melting point. Because this time region, when we're talking about 3 dimensions in the time region, we are 3 dimensions of time in the time region, we're talking about the solid state of matter. So this is all in the solid state. Even these gases like neon in the solid state up to the melting point. The specific heat curve of a hydrogen molecule is likewise a single straight line, but hydrogen has no rotational specific heat component at all. And this line therefore extends only from the negative initial level, minus 1.32, to the specific heat of the positive initial level, plus 1.32, at which point melting takes place. The specific heats of the binary compounds based on the normal orientation, simple combinations of division 1 and division 4 elements. Division 1 are the electropositives with a valence of less than 4 or less, and division 4 are the electronegatives with the valence of 4 or less. So they readily combine those two different groups. Simple combinations of division 1 and division 4 elements follow the same pattern as those of the electropositive elements. So he's looking at compounds, calls those binary compounds. In these compounds, each atom behaves as an individual thermal unit, just as it would in a homogeneous aggregate of like atoms. The molecular specific heats of such compounds are twice as large as the values previously determined for the elements. Not because the specific heat per atom is any different, but because there are 2 atoms in each formula molecule. Okay, so now he shows showing the specific heat for hydrogen, and then he gets into this potassium chloride and calcium sulfide. The curves for potassium chloride and calcium sulfide illustrate the specific heat patterns of this class of compounds. Some binary compounds of other structural types conform to the same regular pattern as in the curve for silver bromide, also shown. As in the elements, there is also a variation of this regular pattern in which certain compounds of the electronegative elements have a higher initial level, but in the compounds such as zinc oxide and tin oxide, this level is 0 rather than the negative 0.66 as it is in the elements. Some of the larger molecules similarly act thermally as associations of independent atoms, such as calcium difluoride and iron disulfide are typical. More often, however, 2 or more of the constituent atoms of the molecule act as a single thermal unit. For example, both the potassium hydrodifluoride molecule, which contains 4 atoms, and the cesium chlorine tetroxide molecule, which contains 6, act thermally as 3 units. In the subsequent discussion, the term thermal group will be used to designate any combination of atoms that acts as a single thermal unit. Where the individual atoms participate in thermal motion jointly with groups of atoms, the individual atoms will be regarded as monoatomic groups. On this basis, we may say that there are 3 thermal groups in each of those molecules, the potassium hydrodifluoride and the cesium chloride tetroxide. The great majority of compounds not only form thermal groups, but also alter the number of groups in the molecule as the temperature varies. A common pattern is illustrated by the chromium chlorides. Chromium dichloride acts as a single thermal group at very low temperatures. chromium trifluoride as 2. The initial specific heat levels are minus 1.32 and minus 2.64, respectively. There is a gradual increase in the average number of thermal groups per molecule up to the first transition point, at which temperature all atoms are acting independently. At the initial point of the second segment of the curve, this independent status is maintained. And above the transition temperature, the chromium dichloride molecule acts as 3 thermal groups, while the trifluoride molecule has 4. At the present stage of the investigation, we can determine from theory the possible ways in which a molecule can split up into thermal groups, but we are not yet able to specify on theoretical grounds just which of these possibilities will prevail at any given temperature, or where the transition from one to the other will take place. The theoretical information thus far developed does, however, enable us to analyze the empirical data and to establish the specific heat pattern of each substance. That is, to determine just how it acts thermally. Aside from some cases mainly involving very large molecules where the specific heat pattern is unusually complex, and in those instances where experimental errors had lead to erroneous interpretation, it is possible to identify the effective number of thermal groups at the critical points of the curves. Once this information is available for any substance, the definition of its specific heat curve is essentially complete, except for the temperature scale, which the determinants of which will be identified in the next chapter. Where N is the number of active thermal groups in a compound, the initial level is minus 1.32 N. The initial point of the second segment of the type 1 curve is 3.89 N, and the first transition point is 4.63 N. Now that's important to note. He's forming a temperature scale here, but it's on the unit temperature system. So in the next chapter, he's going to be identifying the actual temperature values. These are based on a unit temperature scale. So, but there is no conversion from the unit to reality. So he'll be doing that in the next chapter. So we're going to cut it off here, and we're going to take over tomorrow at this point. So thanks for tuning in, and have a great day.